All right. Well, thanks everyone for joining this week's Tech Talk. Today we're going to be talking about computer vision. My name's Sawmill. Before we dive into the full talk, I would like to discuss some upcoming talks. So we'll go over today's agenda on the next slide. But next week we've got a great talk coming up on gRPC uh, and how Mozzie uses it throughout its microservices. And the following week we're going to have a pretty cool talk on running AI models at the edge, why you might want to do such a thing. What are sort of the benefits of that and the way that Mozzie handles that as well. So make sure to stay tuned for those. All right, so today we're going to start with going over computer vision history, where this all started and how far it's come. We'll then talk about some of the most popular tasks within the field of computer vision. We'll go over some use cases and then jump into some fun demos. So this all kind of started 60 plus years ago. A couple of neurophysiologists, they did a pretty cool experiment. They placed electrodes into cats, their primary visual cortex region of their brain, and started to show them various images and tried to see how their brains reacted to it. And what they found was that they detected a neuron firing as they were sliding a new image into the projector up on the screen. And they continued doing these experiments, and their conclusion was actually that there are what they called simple and complex neurons with both linear and nonlinear reactions, respectively, to visual structures such as edges. Right, so the edge of the slide that they were sliding into the projector was able to produce that reaction. And that's a concept that we're going to see in a couple of decades was built upon, and it really helped people try to understand the way that brains process visual information. So store that away for now. Let's move to the early 1960s. An MIT professor, very ambitious professor, I should say, launched this summer project with kind of two main goals. The first goal was to, he had a group of students and he said, all right, you've got a couple of months, figure out a couple of things. First, can you come up with a platform, an algorithm to kind of segment in a general fashion across different types of images, foreground objects versus background objects? And second, can you extract all of the non-overlapping objects from within the image? And again, in a couple of months. And now, as we found out later, this is actually much more difficult than that professor anticipated. This project was not successful. They weren't able to come up with that solution for those two sort of objectives within a couple of months. But this is often considered the birth of the field that we now refer to as computer vision. So it was an important project. Now, fast forward a couple of decades, early 1980s, a British neuroscientist comes up with this framework of understanding the way that we process vision in a hierarchical fashion. So what did he mean by that? Well, we start with low-level information, such as edges, curves, corners throughout the image, etc. And then we move on to a little bit higher-level information, surfaces, depth, discontinuities throughout the image. And the idea is that we use that lower-level information to incrementally build up a higher level understanding of the content of the image. And again, that's another concept that folks in the coming decades would build upon. Around the same time, a Japanese computer scientist named Kuniko Fukushima, I hope I pronounced that somewhat correctly, built an artificial network of those simple and complex neurons that we referred to earlier, and he included what are called convolutional layers. In which we slide what are called filters across pixel arrays. And we represent images numerically as arrays of pixel values. So we slide these filters across those images, we perform calculations, and they produce activations, which kind of represent neurons firing. And we feed the output of a particular layer in this network to the next layer. And if you're familiar at all with neural networks or convolutional neural networks even, you'll see that we're kind of building towards that concept incrementally. So fast forward a bit, late 1980s, early 1990s, a French scientist applied what we call backpropagation to Fukushima's network. And what this did is it enabled learning. So at a high level, the way that this works is, let's say that you've got an image classification task. You want a model to be able to predict whether an image is of a cat or of a dog. Well, based on the prediction and how far off it is from the actual truth, we are able to calculate an error. And through backpropagation, we're able to update the parameters throughout the network so that the network incrementally learns to become better and better at performing its task. And this is what we refer to as learning. So he eventually released a neural network architecture, convolutional neural network architecture, called LUNet 5, considered the first model CNN. CNN means convolutional neural network. And he applied this network to the task of character recognition, right? Can this model look at an image of a character and tell us what it is? Is it an A, B, C, 1, 2, 3, etc.? And he used this to release a commercial product. It was a zip code reader. And his work eventually resulted in the creation of a very, very popular benchmark dataset called MNIST, which is used for benchmarking character recognition algorithms. So that was really a huge step forward, as we'll see in a little bit. Those concepts were really used by computer vision scientists later on. So in the 1990s, later on, David Lowe from the University of British Columbia came up with this concept of features. So he published a paper called Object Recognition from Local Scale Invariant Features. Now these features were things like edges and curves, and they were supposed to be invariant to things like rotation, location of a particular object within the image, the scale of the object within the image, etc. And supposedly this was inspired by properties of neurons in a particular region in primates' brains. So you can kind of see a theme. Folks are trying to understand the way that creatures process visual information and then build frameworks and algorithms for computers to do the same based on that. All right, let me go to the next slide here. So in the early 2000s, sort of building upon that concept of features, Viola and Jones built the first real-time face detection framework, which was not a deep learning algorithm. Deep learning referring to neural networks with many, many layers. It was not one of those, but it did perform face detection in real time, so pretty big step forward. But again, this used handcrafted features, such as edges and curves, for example. That helped it find faces, and this is still in use today. So later on, the Pascal, in that same decade, late 2000s, Pascal VOC project was launched, and that was a competition along with the corresponding data set, which became very popular. It has been used for many popular, or benchmarking 3 popular computer vision tasks, which we're going to talk about on the next slide in more detail. But those are image classification, object detection, and semantic segmentation. A couple of years later, another competition launched called ILS VRC, and along with that was the ImageNet dataset. And I can't really overemphasize how important this dataset has been to computer vision. It consisted of over 1 million images, 1,000 across 1,000 classes of objects. And for years, folks with different types of algorithms were getting around a 26% error rate, an increase, or I should say decrease in the error rate of like 0.1 or 0.2% was considered a huge accomplishment. And then in 2012, a team from the University of Toronto achieved a 10% improvement in the error rate, which is huge, with their architecture that they called AlexNet. This was a convolutional neural network. They trained it on a graphics processing unit, which is a processor traditionally used to generate graphics, but we've found a lot of parallels between those computations and those required to train convolutional neural networks, specifically around parallelization. So they used a GPU to train a convolutional neural network, got a huge increase, and those features are learned. They're not handcrafted, such as the ones in previous algorithms. You basically put into place a network with convolutional layers, and we allow the network to learn which features are most relevant to performing their desired task, rather than trying to figure out, hey, we should look for edges or curves or things like that within the image and handcraft it that way. So that kind of marked a sort of ideological shift. Maybe CNNs are much better suited for these sorts of tasks. Then in the late 2010s into the early 2020s, we've seen so much progress, so many awesome papers published, so many awesome architectures released for different computer vision tasks, really enabled by advances in hardware. specifically NVIDIA GPUs and how much they've advanced over the last decade or so. And this rule doesn't always apply. There are certainly exceptions, but we found that bigger data sets, more complex models, more training time, the better models are able to perform their desired tasks. So we see techniques coming out to speed up model training. Again, these are pretty computation intensive, so anything that we can do to speed up convergence, we should. So we saw a lot of those techniques coming out. We see newer deep learning algorithms coming out for different machine learning tasks like object detection, segmentation. We're able to generate synthetic data, for example, using GANs to generate really realistic looking images of people's faces that kind of are almost indistinguishable from real images. We look at explainability, so new techniques came out to be able to understand which region in the image was most important in a model's decision. Things like self-supervised learning and being able to run these models at the edge. So could have listed a lot more bullet points here, but we've really made a lot of progress over the last decade. So that's kind of the history of how we've gotten to where we're at today. This is not an exhaustive list, like my note says at the top here, of computer vision tasks. There are many more, like image captioning and object tracking, but these are kind of the most popular. Starting on the left, we've got image classification. Can the model look at an image and tell us what it's looking at, considering the image as a whole? So this is an image of a cat. So then we can go a step further to object detection and say, can you tell me where the objects are within the image? And what are they? So we've got two dogs and a cat here, and we've got bounding boxes around those objects. So the model would tell you the top left corner is at these pixel coordinates, and the bottom right corner of that object is at these pixel coordinates. And then instance segmentation takes that even further, and rather than just drawing a box around the objects, we can get an outline of that object within the image. And semantic segmentation, we want to assign a class meaning in this case grass, cat, tree, or sky, to every single pixel location within the image. So these are four of the most popular computer vision tasks, and we can see some of these examples on the next slide. So here are just some applications of computer vision. On the top left, we've got predictive maintenance. Looks like this algorithm detects rust. So can we identify these potential issues and prevent disasters from occurring using computer vision? That's an object detection algorithm because it's drawing bounding boxes around those regions of rust. Self-driving cars use a lot of computer vision algorithms to understand what they're looking at and make sure they don't run into people, read traffic signs, stay within the lines, those sorts of things. Defect detection in manufacturing. Can we automate identifying defects in parts that are being manufactured? So you can see the region, the defect region within the screw here. Medical imagery at the bottom left. We can look at medical imagery, and this looks like a segmentation algorithm to detect things like tumors. So that can help doctors a lot. In the middle one on the bottom row, crop yield monitoring. So being able to monitor the crop yield by basically just running a camera feed through. And inventory management, looks like we've got a bunch of orange juice here. So can we automate kind of monitoring the inventory in a store, for example? And then maybe, once things are running low, someone is alerted and they can either refill the shelf or they can put in a new order. So those sorts of things. I personally would like this in my fridge so that I can monitor when my milk is running low and maybe even put in an order, but it might already exist, I don't know. So that's kind of the end of the slides. I want to pause here and see if anyone has any questions before jumping into any demos. Okay, no worries. So we've got several computer vision models deployed to Modzy. And because Modzy is an API-driven product, we are able to integrate them into many products that people might be using already in their day-to-day work. So for example, this one's ArcGIS. Software. GIS stands for Geographic Information System. And here we've got some overhead imagery. And basically, we've built an integration directly into the software to be able to submit this imagery to a building detection model running on Modsy. And we're going to be able to display the results right here within ArcGIS itself. So we specify the imagery, we press run, it'll go ahead and submit to the model, get the results back, and then display them. This is an example of an instance segmentation model, so we're getting the outlines of the buildings within the image. And as you can see, they're quickly displayed right here. So it's super easy to use. Analysts don't need to deviate too far from their day-to-day workflows. Here's another example. So let's say we want to track a vehicle within drone imagery. Maybe this guy did something bad and the cops are looking for him. Who knows? But here we're submitting this video, and the model running on Modsy is processing frame by frame and keeping track of that red car. And as you can see, it does a pretty good job at different parts. As it moves to different parts of the frame, different zooms, even when it goes into shadow, it's able to keep track of the vehicle. It's doing a pretty good job. The next example that I've got here is Tableau. So Tableau is pretty popular data visualization software. Here we've got some more overhead imagery. And we've got our vehicle detection and aerial imagery model running on Modsy. So basically you submit overhead imagery, and this is an object detection model, so it's going to give you those XY coordinates of the bounding boxes of vehicles detected within that imagery. And we're going to just kind of skip through here. So within Tableau, we point to our images. We've written a simple script to be able to read those images in, submit them to the model, get the results back, and display them directly within Tableau itself on the map. So here we're configuring our script. Let me skip forward a little bit. In Tableau, we point to our script, we run the workflow, and in a second here, we're going to jump into Modsy and see that those jobs are actually processing. So here it's running the flow. Here we can see some new vehicle detection jobs have been created. So it's processing chips of that overall satellite imagery. The flow has completed, and we're going to go ahead and visualize them right within the software itself. Now, I did mention this is an object detection algorithm, so it does bounding boxes, it returns bounding boxes, but for purposes of visualization and not to clutter things up too much, we're just taking the center point of those bounding boxes and displaying them. And as you can see, it did a pretty good job of finding a bunch of cars. You might want to do this sort of thing maybe just to monitor parking lot capacity. I know retail investors sometimes look at this sort of thing to kind of understand how many customers are actually going to these stores. So a couple different reasons why you might want to do this sort of thing here. And I briefly touched on explainability earlier. So, you get these classification predictions, for example. The model says this is a cat, this is a dog, but you want to understand why and make sure that the model is making those predictions for the right reasons. So here we've got a model running on Modsy. It's automobile classification, so it looks at a picture of a car and tells you what car it is. And we can see here with our explainability technique that the reason that this model predicted that this was a 2012 BMW M3 Coupe was because of the shape of the hood. Maybe the BMW logo is included within that mask. And this really allows you to understand why models make their predictions and subsequently or consequently gain trust in that model. Right? It could be the case that in the training data set, these M3 BMWs were always next to light posts. And so in that case, you would see the explainability mask on the light post, but you know that the model is not making that decision for the right reasons, and maybe you need to consider retraining. But here, it looks like a pretty reasonable reason why the model might make its decision. So those are just a couple of sort of real life examples running on Modsy of computer vision. And I think that is all that I had to show. So I guess I will stop here. And if anyone has any questions, I'm happy to take them.